Okay, give me one more. Okay, fine. I hope slides are visible. Again, welcome to Machine Learning for Material Sciences. So today we will discuss on convolution neural networks. So previously, just a quick reminder, we looked at very classically, we looked at AI, then classical machine learning, regression, classification, gradient descent. Then how do you feature engineer for machine learning? Then we looked at ensemble, and then we jumped onto neural networks and like various portions of what are the advanced architectures for neural networks and how do you basically train neural networks? Some of the newer techniques that we have, what are the problems we have, how to correct those problems. Yes. And today we are just going to discuss one more variation of convolutional matlab neural networks. This is a little bit more popular in image sense, but as I will discuss, this is like also very important when you have something called like a spatial locality relationship. Yeah. Typically, these are, of course, like as I've written, like specifically they're used for images, like how computers can actually recognize, face images, how they can drive cars, yes, and how can they diagnose diseases from pictures and all this stuff. CNNs have been at the heart of all this for a very long time. Till now, also CNNs rule. There are some cases where transformers have taken in some particular use cases, but still CNNs have ruled for very long time. Hmm. Uh, so, like computer vision as such, this is another word that keeps on coming is called computer vision. Uh, that's also like very synonymous with like images and computing and all that stuff. But CNN itself uh, made sure that computer vision now has become from an engineering problem, it becomes a machine learning problem. Yeah. So, and it was the first kind of problem where deep learning itself showed its strength. And so the concepts that we will learn today will be like fundamental to that particular modern AI, let's say. And hopefully by the end of this class, you will understand like why CNNs are so effective for visual data and how the convolution operation works, let's say mathematically, and how do you calculate this parameters and output sizes. Yeah. And so we will move from motivation to maths to practical implementation. Yeah. Fine. So we'll start with a problem. So let's say the goal is basically you want to use a very regular neural network. Fine. I hope you remember the regular neural network bunch of graph that looks like nodes in every layer, input layer, hidden layer, and output layer. And what we have is basically a multi-layer perceptron or MLP for image classification, right? Uh, Eventually we'll end up with a bigger problem, right? So if we try to use MLP for image classification, what will happen? Let's say if a tiny image is there, 32 cross 32 RGB image. Now, because it's an RGB, that means every pixel has a red, a green, and blue color parts of it. So if we connect, that means the total number of input features will be like 32 cross 32 cross 3. That becomes 3072 pixels. Now, if we connect this to around just 1000 neurons, right? So if we just connect to 1000 neurons, uh, basically the input layer is 3072 and the middle layer becomes 1000. That the hidden layer size is just 1000 neurons. That itself becomes around 3 million parameters. It's already too big. Now imagine that it's not a 32 cross 32 because the images that you have are too big. But assume, let's say we go a little bit bigger image, 224 cross 224 image, which is basically a 224. 224 was your old school like Nokia and all that stuff. So that had that kind of resolution, 186 cross 106 and so on. So this becomes like 150,528 input features, right? With the same 1000 hidden neurons, you will have over 150 million parameters. Just input layer and the second layer, right? We are not even adding more layers. So that means like if you have this, you just, it's an exponential parameter explosion problem, right? Explosion problem. So mathematical challenge here, basically historical. Oh, one historical example also, like when, for example, AlexNet came in like 2012, let's say ImageNet. Yeah. It's the AlexNet, ImageNet was a dataset that was built up for all this tasks, computer vision tasks. And AlexNet basically won the cup, or let's say the challenge in 2010. The cup is called ImageNet itself. And it used basically 4096 hidden units, right? So now assume AlexNet used only 4096 hidden units. If that was like just we used MLPs to solve that problem, we would have 606 million parameters, right? And that is just one layer, right? This is just like completely impractical to train so many number of parameters, right? It will take a long time. It will use compute. It will overfit immediately, right? And it will not, and you will not even find a GPU that can actually push 616 million parameters. Oh, sorry. Huh. So now then what do we do, right? So then this is becomes the fundamental problem that we have in MLP, specifically for images. Yeah. And there is no concept of, let's say, reusability. Yes. Or like same spatial structure that we can do. So that was basically the key motivation why MLPs could not be used for images, parameter explosion problem. Now let's understand like a little bit more. So one of the problems that we have, not problem, let's say, one of the importance we have is basically translation invariance. So now imagine a picture, right? So of a cat in a top left corner of an image, right? And if the same cat, same size and same pose is on the bottom right corner at a different position in the picture, to us, it obviously looks like, okay, it's the same cat. But for MLP, what will happen is it will become a completely different input because the cat was in top and the cat was in the bottom right, right? Why? Because now every pixel will have its own unique weight, right? So because of that kind of relationship that we are building with MLP, now for us, cat anywhere is still a cat, but otherwise it just becomes like too big of a problem for MLP to tackle because MLP does not understand spatial locations. Yeah. So what do we have? Yeah. So now the next feature is like local feature detection. So in local feature detection, what we have is like, let's say, edges, corners, and textures. These are local patterns, and MLP uses global connections. Yes, and they cannot efficiently detect local spatial patterns that we have, and because every pixel will connect to every neuron. Yes, uh, it's like trying to understand every word, right? We are trying to put every word basically rather than phrases. Yes, because phrase is important in like language. Similarly, a portion of, sorry, pixels is important for images. So what do we need? And okay, sorry, one last problem, like the MLP will flatten basically the entire 2D image of rows and columns of pixels will become a single vector. Yes, 1D vector. So then whatever was in the first could have mapped could be closer to the 21st. Let's say there are 22 pixels in a single row. The first pixel would have matched with 22nd pixel. It would have been closer. But in MLP, this becomes flat. So that means there becomes a distance. So it loses the spatial relationship that was there between the pixels. And adjacent pixels are treated as same as distant pixels. So it doesn't make sense. So MLP basically does not work. So what we need is an architecture that will share weight across positions that will use local connections, that will preserve spatial structure. Yeah. And this architecture is the CNN architecture. Yeah. So we'll just look. So some history, like CNN, of course, was not invented in a vacuum. There was some relationship that happened, right? So, for example, 1962, we understood key, like, if you have they did an experiment, of course, like Robel and Usel, they won the Nobel Prize for it, of course. And they discovered the neurons will respond to edges in a very specific orientation, and the one neuron fired for vertical edges and another fired for horizontal. That means there are different types of neurons that are specifically trained, let's say, which look at vertical and horizontal edges, right? And then there will be another edge to look at a 45-degree angle edges. So these are called simple cells, rather they are like edge detectors. Yes. And so there is also another level of understanding from their work was basically there is a hierarchical approach to solving this image problem itself. So that means low level neurons will basically detect simple features, higher level neurons will combine these to ask even complex questions, and at the top, they will just give you basically higher level or specific objects or faces. Yeah. So what we have there, we have key inside, local receptive fields are there, feature detectors are there, and hierarchical representation. This basically led the path for CNNs. So CNN design principle follows exactly the similar thing: local connectivity, parameter sharing, and hierarchical learning, right? And basically, Yang Lee Kun was, I hope you have might have heard his name. So basically, Linet was implemented based on these kind of ideas. Yes, and it was specifically done for digit recognition. Basically, the MNIST, the number, handwritten numbers, they were able to do so. Yeah. But the CNNs actually became very big after 2012 when AlexNet won, basically. And compute has to be given the goal. So now before just jumping to images, we will just quickly go over convolution a little bit more mathematically, right? It's a very fundamental to signal processing. And if you look at this first equation, like the 1D convolution, here F will be your basically input signal. That could be like audio, let's say, or any time series. And your G will be the filter or the kernel. Okay. This basically modifies the input signal. And the star, that means basically is a convolution, not multiplication. Right. And what we are doing is essentially we are trying to slide G on top of F. So F is given to us, and then we are just sliding G on top of it. Yeah. So, and each time point T, we basically flip the G because G is T minus tau, and we slide it to the position of T, and then we compute how much it overlaps with the function F, right? So we match when G is the kernel or the filter, we reverse the T, basically we flip the T, and we say how much you are equal with the function, right? So every time step we do the same checking. And this is also equivalent to if we give a task to anybody to find a particular pattern in the picture, they will do the same thing, right? You will try to take a filter, try to mask it over some areas. Okay, is it able to completely hide or not? Yeah, that's a similar type of question. Now, and 2D convolution, again, you can extend it to it. And key property here is convolution is commutative. That means you do F star G is same as G star F. Okay, so that means the order does not matter. Yes. Conceptually, it might matter. Actually, it does, but mathematically, it does not matter. Yes. And only difference here is it is a continuous function, and the images itself are discontinuous. Most of the signals that we collect are discrete, right? Even if you see analog, they are like discrete converted to analog. So Hello. Sorry, I guess it got disconnected. Was waiting also for a while. Fine. I don't know where it got disconnected. Yeah, I'm assuming it got disconnected here. Uh, s- yeah. Uh, yes, I think for 2D convolution, we discussed like this is a continuous, and then for the discrete, what you would have is basically this CNN particular operation. And is the same integration basically converted to summations, and the process is almost similar, and K becomes a kernel, image convoluted with the kernel becomes this. And so here I hope like if somebody can confirm me as well on chat if they can hear me, that'd be nice. uh, and then like we'll go with one example that we'll have. So this is, for example, let's say we have an input image. uh, I'm audible, right? So if anybody can. Hello.
Yes, sir.
Okay, okay, fine, fine. Thanks. So now, like, what we have is like an input image. Let's say it's a 4 cross 4, like matrix, because like images eventually they are numbers. So you can assume this is a gray and like gray image, where 0 is basically black, 1 is gray, 2 is completely like white, let's say. And let's say we have a kernel 3 cross 3 kernel, which looks like this, like ones and then zeros and then minus one. So how do you calculate the new position of 0 comma 0? Initially it was 1. You can apply the formula basically of the convolution formula that we learned here. And so I convoluted with k at 0 comma 0. We'll apply this two summations over IUV and KUV, and U and V will vary from 0 to 2. This is assuming like, the size of the kernel is that much. And then what we have is the output is basically 2. Now, initially the value was 1. Now the output becomes 2. Yes. So that's how you do like CNN convolution. Yes. And then you could have like different kernel types. So one of the kernel types I showed you here, but technically you can have some fixed kernel types that can detect very particular set of features that you would want, right? One of them is vertical edge detection, that is all columns one, then zeros, and then minus one. If you apply it across the image, like slowly, 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 what will eventually happen is all the vertical edges will be highlighted, which is not vertical, they will not be highlighted as much. Then there is horizontal, like ones, zeros, and minus ones. If you apply this filter, then everything will become 1, 0, like if all the horizontal edges will be highlighted. Then there is Gaussian blur, then there is sharpening. Gaussian blur basically what it does is basically you can assume a 3D Gaussian. Middle point will be high, then will be a little bit low, then outside will be lowest. So it basically increases, it applies a blur, which the middle point becomes basically brightest, and so on and so forth. Sharpening basically, it basically tries to find out the maximum difference between myself and the neighbors. So it tries to increase the contrast way too much, let's say. And so here, if you look at it's 5, and the middle point will be very high, and then immediate neighbors will be low, right? So it's 5 and then minus 1, and outside will be can be 0. What it tries to do is increases the distance between me and immediate neighbor. And now if the kernel gets applied, what happens is, and if you have something called a stride, then the output size of the images will increase or decrease. Basically, decreases, increasing is possible, but not with just the kernel. So there is something called a stride. Stride is basically if you have this image, your kernel keeps on moving, right, from one place to another at the time step t. What was the change in the position? If it change in position is let's say 1, then stride becomes 1. Kernel moves 1 pixel at a time. Stride 2, kernel will move 2 pixels at time. But if it starts moving 2 pixels at time, then it will reduce the output size, right? Uh, then what we have is basically the padding. If we want to maintain the same size of input and output, then we have to do something called padding. Yeah, specifically because we are doing a stride. So without padding, then the output size will decrease. With padding, we can technically maintain and even control what should be the output size. So the output size is given by this method, let's say, this formula. So W minus F plus 2P over S, let's say. So all the input width, filter size, padding, and then stride. Yes, everything is included here. One of the example is, if let's say the input is a 32 cross 32 image, the filter is a 5 cross 5, and then padding is 0 and stride is 1, then the output size will become 28 cross 28. So there is a loss in image size. But you could technically do a padding of 2, then that increases the size of output image. That becomes 32 cross 32. Basically, you started with 32 comma 30, 32 cross 32, and you ended with 32 cross 32. Yes. So now you have learned four things. So input, kernel, then stride, and then padding. Fine. With that, there are two more things that we'll study. Basically, one of them is basically convolution across channels. So channel is a thing. So if you look at color picture has basically three channels. So red, blue, and green. There can be more even like RGBD. If there is a depth camera, you can have RGBD. You can have as many channels as possible also depending on what is in. For example, hyperspectral images, they have more channels as well. Every band of frequency becomes a channel. Yes. So but at least the general pictures, they are RGB. So what you have to do is you have to convolution across channels. The formula is given by this. Everything remains the same, but you do a channel convolution as well. Yes. The other one is you can, in a single picture, let's say, in a single input phase, you can do multiple filters. That means you can look for vertical edges, you can look for horizontal things, you can blur, and you can find 45-degree edges. All of them can be done in from a single input, right? But every time you apply a particular kernel, you get an output, right? So for one input, and for two kernels you will get two outputs, right? So here is the same thing. So if you had one image but n filters, you would have get n outputs. Those n outputs are called n feature maps, right? So now each filter is basically learning different features. So one for, let's say, vertical edge, one for horizontal edge, and so on, so forth. Yeah. uh, uh, Okay, so now the next is like, how does a total convolution look like? So this is basically looks a very little bit complicated, but this is everything that we have studied before. If you looked at the innermost two summations, that is the 2D convolutions. If the outer convolution is over channels, the BK is the bias that we generally add. The K is specifically for the kth filter, and then the sigma outside is basically the nonlinearity that is applied. Yes. And then we can calculate parameters as well. But just to give a highlight, like what is the difference between CNN and MLP? So an MLP basically connects every input neuron to output neuron in the same, like let's say the input neuron in one layer to the output neuron in the next immediate layer. And this is exactly why we have basically explosion, right? And there is no special structure in build, and parameter count basically explodes. But in CNN, we have shared weights. The shared weights are basically the kernels, yes. And basically, that kernel keeps on moving across the entire image rather than one particular weight for particular neuron. Then there is a translation equivariance. That means, like, if there is a translation that is applied to the image, the function's output uh, after translation, before translation will be the same, right? So we have an equivariance equation there. And then parameter count is basically does not depend on input size and hidden size, rather it is filter size square, channels, and number of filters, right? So, and in empirical sense, this is way lower than MLP. And if you see like a comparison, if you had a 28 cross 28 grayscale image and you had 32 filters, each of size 5 cross 5, CNN would be like 30 times less parameter. Right? So it's a huge drop, 25,000 compared to 832. Yeah. And so this was the image, let's say. So if you had the image was on the left hand side of this thing, and if you look at the kernel, it's a 2 cross 2 kernel. And the 2 cross 2 kernel basically is once it is on top of it, on the image, you get an output, right? And that output basically goes there. I will talk to you about pulling a little bit. And the stride is how the kernel moves, right? So here the kernel is moving by two spaces. Yeah. The next is, let's say, the pooling itself. The pooling function, there are many pooling functions, and but the most popular ones are ones that are easy and perform really well. Easy in compute as well as easy to understand. One of them is max pooling, the other one is average. So, for example, a filter stacks here. Each of the filter weights. So, for example, if it's a 2 cross 2, if you look at this particular image, wherever the slightest blue is there, if you look at this on the previous layer image, let's say this, how do I say, the light blue, and the kernel is, let's say, the deeper blue on the top. The same square, like the same square, 0 comma 0 in the picture and the 0 comma 0 in the kernel, they get multiplied. 0 comma 0 in the picture is the shaded portion, and they get multiplied. That's how you get kernel. But the final value that you get is just a single value because you are pooling information together. That information pooling can be done in many ways. One of the most popular one is max pooling. That means you do this multiplication 0 comma 0 with 0 comma 0, 1 comma 0 with 1 comma 0 of kernel, and so on. And of all the values, you take the maximum value. That means the maximum information is getting extracted, right? But still, or you could do average pooling as well. But the only problem is you're still losing some information, but however, you are still extracting the maximum information out of that. Fine. And uh, yeah, and then pooling introduces basically another feature also, that where there is a size reduction happens, right? Uh, Special downsampling that we call. So I don't know if you have started looking at some image related or resonate related models. So pooling specifically leads to lower sizes of images. There is like, for example, one common configuration is like 2 cross 2 pooling with a stride of 2. It basically ends up with a 50% size reduction, right? So for example, this image, if you look at it, it was, let's say, 8 cross 8, it eventually became a 2 cross 2, sorry, 4 cross 4, right? And but this is a 2 cross 2 pulling with a stride of 2. So it's like 50% of the size gets reduced, right? And the depth is preserved, like the number of channels get preserved. If the number of channels will increase with the number of filters that you have, right? Because every filter will produce one more feature map. But it reduces the dimension of the input in one particular channel, right? And I talked about that. You still lose information. There is some information loss, but it preserves the strongest activations. It provides translation invariance, and it introduces some form of non-linearity, right? So because it's not straightforward to do pooling, and then it loses spatial precision, we tell, because some of the images that were like, neighborhood images, they did not, neighborhood information got lost, right? So because of that, and the pooling has some mathematical information behind it. For example, let's say if you have a 2 cross 2 max pooling with a stride of 2, if your input is this, then output becomes that, then the information loss is basically 75% of spatial information is discarded, right? Uh, you pull the maximum information. Now, after pulling maximum information, you don't know from where it came and who your neighbors are, right? So all these informations are gone. So you have essentially a trade-off between, because this is more generalized, because it introduces nonlinearity and try not to memorize stuff. So it adds to robustness also. But then spatial precision is lost. Translation invariance is there, but then your fine-grained localization is lost because Max itself loses where from the value came. So now a typical CNN will look like the entire architecture. It will have input, you will do a convolution, you will apply a ReLU, and on the top of that, you will do a pooling, and then you have an output. It's a CNN block. You can combine such multiple blocks to form a bigger CNN model, right? Convolution is your Wx into B that we looked at the formula. Activation could be ReLU of that Z, let's say, and pooling could be, let's say, the max pool. Yeah. So I will just show you one of the examples. So one of the examples is here. So let's say we have from bottom to up is how the architecture looks like. If you have an image, let's say C cross H cross W, convolution happens first, then pooling, then again convolution, again pooling, and then you have some, and in between everything you have these sigmoids that basically do the nonlinearity. But after some times of pooling, then you have an image, but eventually finally at the end you still need to answer questions in either it is a, let's say, cat or dog. So eventually it has to be a vector of, let's say, 2 dimensions if there are two classes. So you apply multiple linear layers to reach to the number of classes, right? So here, let's say the number of classes was 10. So we kept on applying linear layers to count down, basically make it the size to be like that many number of classes. So here it was 120, 184, and then 10. This is the output size. You have to figure out like based on the input. So that was the typical block, and then residual connections we have studied before. So those are also applied, and then depth-wise separable. Basically, this basically specifically tells like your input channels, like the features are calculated uh, in abstraction. Like some of the earlier layers, they pick information about the lower scale and all this stuff. So that means there can be a distribution of information gathering across layers. And also we also do spatial level convolutions, and we also do channel wise convolutions. So all these kind of separation is there. So that means there is a opportunity to do parallelization. Fine. And receptive field, I will come back to it. I just wanted to come back to the parameter count example. So let's say we had one layer one that was a 30 cross 32, that was the input size. Then we did a max pool, then layer 364, then we again had a max pool, then we again had some filters with stride and pad. After all this, we had 127,552 parameters. If you look at this, this is a way more computation that we like with less parameters we can do in CNN compared to, let's say, multi-layer perceptron. Specifically because the filters are shared, right? And using max pool and stride and everything, we try to reduce the dimensions further as we go from one layer to another layer. And because of this, and you can also include like activation maps and gradients to count the memories. Translation equivalence is a property of like convolution. I will not repeat it here, like specifically to avoid time here, but this a part of like convolution operation itself is a translation equivalent. This specifically helps on all those information of like where is the cat, and the position of the cat now doesn't matter. Okay? And finally, we want to say this one. So for example, in traditional hand vision, we would like have handcrafted features. That means we'll exactly tell what are vertical things, what are vertical edges, what are horizontal edges, and so on. Feature extraction has to be manual, and then classifier would be SVM and random forest. But now we have moved on to CNN. Now raw pixels become learned features. We have end-to-end learning. That means features are also learned. What features to extract, we learn. Earlier, you used to say, okay, find out vertical edges and horizontal edges. Now we don't say that. We just say that, okay, you find what features are important. It could be edges or not edges. Right? Then we have hierarchical representation, low level to high level, because it does an abstraction. So traditionally, it looks like y is equal to f classifier phi of x. Phi is basically feature extraction, but that we fix. But CNN is more of like FCNN, that is parameterized by theta. We find theta. Yes. And that's basically the summary of this entire thing. So we have why CNN is important, MLPs explode, a number of parameters, what is convolution, how do you calculate the output size, what is multi-channel convolution and parameter sharing, how much is like multiple filters also, and then how do you build an entire CNN architecture using CNN blocks. Um, Quickly, I just want to show you, I know it's 5:30 already, but we lost some time before. So I just want to show you quickly the code. Uh, okay, I have shared this anyways on the website. You can take a look and try. And okay, I hope you can see this. Try to do this if possible. Okay, sorry. Fine. This is basically some of the same libraries we're using. Here is just calculation. I'll come back to this. So this is MLP first layer. I just wanted to show you what is the calculation thing. You can give it a try. Operations are written. You can see like how like 77 million parameters to very small parameters. How do we do? It's not that the CNN is like zero parameter. There is still an increase in the parameter size, but not as much. Yes. And then there are like multiple other examples that I've shown with like what happens when you have a vertical edge detector. How does it look like? Let's say the input image looks like this, and your vertical edge detection looks. Then what happens to your output, right? So it shows you exactly where the kernel moves and tries to find out. Here the input is 4 cross 4 and the filter is basically 3 cross 3. And output input is 5 cross 5 and then our kernel is 3 cross 3 and then output becomes 3 cross 3. And this one is just an example of what happens if you use all those filters that we just looked at, like vertical edge, horizontal edge, Sobel X, Sobel Y. You can take a look what are those filters as well. And what if happens if you have a Gaussian blur. Yeah, so like vertical edge tries to detect more vertical things, horizontal will try to detect more horizontal kind of edges. Uh, and then sharpening will try to sharpen. It always does not work, of course, but Laplacian will try to find, you can find noises that way pretty nicely. And then identity is there, so it becomes exactly the same thing. Yeah. Strident padding is there, like how strident padding will help you. For example, input is 8 cross 8 with strident padding. What is the output size, right? So this is an example where we show basically what happens with particular input. Please give it a try on your own so that you can take a look and appreciate. And here in the next example, we are basically showing if the input is 8 cross 8 and if you have a max pool of 2 cross 2 and or an average pool of 2 cross 2, this is how the output looks like. Right. So, for example, depending on the size as well. So, if the size is 100 cross 100, max pool is 2 cross 2 you used, then the output size becomes 100 cross 150, and you see this much information is carried, and so on and so forth. Right? So, then you can decide what information is coming out. Like every feature map that will go forward will have all those information. You can think of that the max pooling might not give you a lot of information, but it actually tells you a lot of circle a little bit more heavily, right? Because it has a circular, let's say, shape. A cup has a circular shape, a little bit more prominent circular shape. So that might also help. And average pooling also, what is the impact of average pooling on the images, right? And the next one, yeah. So if you have seen my earlier slide where I told you there are convolution layers, then pooling layers, convolution, pooling, and then there are linear layers. So here, if you look at this, like there are still linear layers, right? Those are basically the MLPs, and dense layers. Those are like that means every neuron is connected to every next neuron in the next layer. Then still parameters per layer comes from the fully connected layer. FC layer is the fully connected layer, but the convolution itself has very less layer parameter shares. So if you don't reduce the size of the image, then eventually you will end up with such large fully connected layers. And this one, receptive field, I did not cover there, but if probably in the next class I will jump in. And yeah. So the last one was the parameter explosion thing. I just wanted to say, like, if the image width is increasing on the x-axis, you can take a look. Like CNN with the 64 and 5 cross 5 still remains the same. The number of weights don't increase because all you are learning is the 64 filters each of 5 cross 5. But like the parameters in the neurons will just keep on increasing, right, as the size increases. So and you can try this part of the code as well to help you out. Yeah, fine. So hopefully this gave you some hint of CNN or one of the architectures of neural networks is useful. Like how did they thought about making this friendly to places where spatial locality is more important, right? uh, that's it for like neural network part of it. And I think from next week, Professor Singh will be taking classes. We'll cover material sciences, and we will both cover multiple like papers and study like how they have used machine learning for material sciences. We'll also specifically see where CNN has been used to solve material science properties problems. Yeah. Okay. And if there are any questions, please let me know. Otherwise, please drop an email. And the next class will be on Monday, 4:30. Professor Shane will be taking the class. Okay. Uh, Fine. I guess I think it's already 5:40. Fine. We'll meet on Monday. Bye for now.